Good morning. We continue with our lecture on heat treatment of steel. Now, in the first class, what we did is we revised the few of the items which was covered earlier, primarily the relevant part of the phase diagram of steel and time temperature transformation diagram, which is called isothermal transformation diagram. We also talked about 3 different types of product that you can get depending on the temperature at which you allow the transformation to take place in 0.8% carbon steel. So, in the last class the entire topic was discussed with respect to a definite composition of the steel. And in fact, in short, if we look back, what we covered is this portion. We also talked about 3 different types of product as a result of 3 different types of transformation, and we looked little detail about how the formation of pearlite takes place. We also talked about the nature of that isothermal transformation kinetics. That means, we only looked at the kind of plot that you get, that is fraction transformed as a function of time. And what we found, that there is an incubation period, this type of S shaped curve you get. Any isothermal transformation like the one that you get in pearlite, it starts only after a certain length of time at a particular holding temperature, and it is completed only after a definite time. So, there is a start time, there is a finish time, and both of these are functions of temperature, and let us build upon that further. In fact, if you try to recollect, there is some similarity in the heat treatment process of what we talked about in case of aluminum copper alloy, where we heat the alloy to the single phase region, and then if we cool it fast, you get one kind of structure. If you cool it slowly, you get another kind of structure. Now, if you compare the two, here also we talked about heating the steel, which is initially alpha plus ferrite plus cementite, and here it is alpha plus theta, which is some intermetallic compound of aluminum and copper. So, this is and here this is an iron carbide, cementite is an iron carbide, and in this particular case, so overall heating process, if you look at heat treatment process, you have initially a 2 phase structure, you heat it to this temperature, single phase region, allow it to remain at that temperature for some length of time, then you cool it very fast, you get single phase structure. Here also you get single phase structure, but look at the difference. Here there is both cases, in this particular case there is no change in crystal structure, and there is this and the material becomes soft, whereas in this case the crystal structure changes, and by changing this crystal structure you are keeping by force much more amount of carbon in the lattice, and the lattice gets distorted, and instead of getting, say normally the ferrite is, this is BCC, and if you look at that solubility at room temperature, it is virtually negligible, and if you quench, what is happening? You are keeping almost nearly 1 atomic percent of carbon in the solid solution, and if you do so, then this lattice gets distorted and it changes to body centered tetragonal structure. So, we talked about this last class, and we also see that it is possible to design isothermal heat treatment process by which you can get different mixtures of structure. Suppose if you heat a steel to this particular steel in the austenitic region, quench it to a bath, maintain at this temperature, allow it to transform completely. Here you get Pearlitic structure. If you allow it to transform at this temperature, you get Bainitic structure. If you quench directly, you get fully Martensitic structure, whereas if you have with intermediate hold like this, you hold it here, some amount of Pearlite forms, you quench it, another, and then here also you keep it for sufficiently some time, length of time, so that some amount of Bainite forms, and then finally you quench. Still there may be some amount of untransformed austenite. So, these the in between region actually represents austenite plus transformation product, possibly alpha plus carbide, and cementite is one form of the carbide. So, in this particular case you get a Pearlite, you get Bainite, you get Martensite. Now, what happens in this particular case? Whenever you draw a vertical line, just think you are cooling it at a very fast rate. So, here there is some amount of untransformed austenite. So, that transformation you are suppressing, you are coming over here, holding it for some time. So, there is a likelihood a part of this may transform, and that will depend on the kinetics, whether the complete will transform or it will actually depend on its present structure and also how long you are holding here. And finally, if there is something left untransformed, if you quench from here, it can get transformed into Martensite. So, here also, although it is crossing this line, does not mean that this Pearlite transformation is complete. This untransformed portion will undergo transformation isothermally here partly, and when you quench, the remaining portion will get converted into Martensite. So, here also you will get maybe different amounts, no doubt, from this particular case, but here also you will get 3 different types of microstructure. So, the total microstructure will be a composite microstructure consisting of Pearlite, Bainite and Martensite. Now, let us look at that Pearlitic transformation in little more detail. Say here, say look at this, and if you plot this as was mentioned earlier, that you have quenched it here, then you hold it, you cool some of these, quench from here, 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 and maybe if you look at that microstructure, you will find that in this particular case, this will be 100% Martensite, here 100% Martensite, 100% Martensite. So, all these cases it will have the maximum hardness, and once Pearlite starts forming, the hardness will start dropping and you will get a different microstructure, that is Pearlite you will be able to see. Amount of Pearlite will go on increasing and it will reach nearly 100% over here. And if you plot this fraction transformed by following either this microstructure examination or hardness measurement, you can convert this data into fraction transformed. And if you plot this fraction transformed, you get some kind of this type of an S shape curve. So, initially the transformation is slow, it picks up, it is midway, it is the fastest, and again the growth area decreases. The different nodules, when they try to grow from different areas, when the transformation is nearing completion, they will impinge on each other. So, therefore, that growth process will be inhibited. So, again this rate of reaction decreases. So, this is the nature of this fraction transform, and if you look at that nature, you will find that it usually follows this type of kinetics minus some constant k t to the power n, where n is some exponent, t is the time. And usually this scale is often we use in a logarithmic scale. So, this is how it is represented, and this form in fact it is shown here. I think here, look at, this is the same equation which is written little differently. This is the same equation written little differently. Instead of k, which is outside this parenthesis, we have put tau, t over tau. Tau is some characteristic time, we will come to know about it, and it is tau t over tau to raise to the power n. So, this is a famous Jenner Avrami this Johnson-Mehl Avrami equation, and we will know about it, how it is possible to derive that in this particular case we do expect this type of representation. Now, the question comes, what are the experimental techniques one can adopt to find out this or to know about the transformation kinetics or kinetics of Pearlitic transformation. One I mentioned is the microstructure examination. You do some interrupted quenching from that isothermal temperature, look at the microstructure. On the same sample you can follow the transformation by measuring hardness, and hardness is a function of microstructure. So, when you have Martensite you will have maximum hardness, and when you have Pearlite you will have minimum hardness. So, in fact, if you plot this hardness, say suppose you measure this hardness in our Rockwell scale, and here is the time. So, initially when you quench, up to some time you will find that hardness is possibly around RC 64, and it remains, and thereafter it starts decreasing with time, and finally it levels off to a some lower temperature depending on that isothermal strength, which may be around RC 30. So, here from this plot you can say this is the start of transformation, this is the finishing point of the transformation Tf, this is the starting point of the transformation. Same thing is possible with resistivity, and also it is possible to follow this type of transformation by measuring the change in length. Whenever any phase transformation takes place, the crystal structure may be changing, there is a redistribution of solute element which results in change in length. So, this also can be used, and we all know when we talk about transformation, always there is some energy change, some enthalpy, that heat, either it is exothermic or an endothermic process. So, if you can measure some calorimetric study, so differential scanning calorimetry or thermal analysis can also be used to follow the transformation kinetics. Now, a point about the nucleation and growth process. Now, here look at that nucleation, and schematically it is shown over here. You have a certain number of nuclei which has formed, and with time two things can happen. One is, if these nuclei they are stable, their size is greater than the critical size, they will grow. So, which is shown over here, this nuclei is growing, and simultaneously fresh nuclei, stable nuclei may also form. So, two things take place parallelly. So, you have nucleation going on, you have growth of stable nuclei. So, two processes they take place parallelly, whereas we can also think about a process like this. Say, okay, we say that there are only certain specified site where nucleation can take place, and only after all these sites are having some precipitate or some transformation product, only then the subsequent transformation will take place. So, that means this is initially nucleation takes place, and when all nucleation sites are saturated, then only growth process sets in. So, this is that kind of a process. And finally, towards the end also in both cases, either here and here, it will also come up with a situation when these keep growing, and ultimately this transformation will also depend on this impingement factor, something like this. Say suppose here these are growing, then they start, a stage will come when they start touching, and finally you know they start touching. So, here this growth in this direction is inhibited. So, this will grow in this direction, this can grow in this direction, and ultimately you know this grows, and by the time this grows comes up to here, maybe this also will grow, they come, and you have this kind of structure developing. So, that means this is impingement is also an important factor, and this thing shows up towards the end of the precipitation or transformation process. Now, a quick look at this process which is shown over here. So, imagine, so this is one nucleus which is growing, this is one grain which is growing, this is the another which is growing, and this volume is V1, this volume is V2, and let us say this is the volume of this total space is V total Vt. So, fraction transform you can estimate it sum of V1 plus V2 over total. And now, so this we call, if there is no impingement, we can call that this is true volume fraction, whereas in this particular case, if we do, what will you get? You see there is a area where these two are overlapping. Nevertheless, we can still calculate a volume fraction based using the same expression as over here, and which is done. And now, you expect, and you really you can clearly visible that, and it is evident that this volume fraction transformation, this fraction transform will certainly be higher than the true fraction transform. So, we call this extended volume fraction, this or you extra volume fraction, this is there is something extra, the true plus something extra is this. And is there a way of finding out? So, that means if you look at, say suppose we say that there is a relationship, there is a small increment in true volume fraction, and there is a small increment in this extended volume fraction. Now, these two, they will be nearly equal when volume fraction is very close to is very low. Chance of impingement is remote, but when f approaches say 1, in that case what should happen? Then this increase in true volume fraction will be extremely low, it should tend towards 0. So, that means df should tend to 0. So, that means one relationship that obviously that becomes obvious, that this is likely to be given by d, this is f x extended volume fraction 1 minus f. So, you look at it, if you put this as 0, both are equal, whereas if you put when it is approaching 1, then you see there is a large difference between the two. So, this is approaching 0. So, therefore, where this offers a simple method of finding out the relationship between fraction transformed, and which can be done very easily. Say, how will you do it? See, in that case, what we can assume, say if you make some assumption, suppose we make this assumption, that is site saturation model. That means, you have fixed nucleation site, you have only n number of nucleation site, and once all these n nuclei they are formed, then only growth sets in. So, you can easily find out, say suppose if the radius of that nucleus is r. So, your volume will be proportional to this, which is 4 pi by 3 r cube. So, this is the volume, and if we say that there are n nucleus of this type, so you multiply this with this. So, therefore, this we can say is equal to the extended volume fraction. And if we assume that there is a growth rate is constant, that means R increases linearly with time. So, suppose this G dot is the growth rate time. So, if you substitute this here, you get an expression for extended volume fraction. Now, to get D extended, what you need to do is differentiate this expression. This is a function of time, you differentiate, and this we know is equal to f over 1 minus f. And once you substitute this over here, then you can integrate and get that expression, and which is shown over here. Look at these steps. So, here these are the nuclei, fixed number of nuclei, and this is what has been done. You have certain fixed number of nucleation site, and once these all sites are saturated, this is the extended volume fraction. Differentiate it with time, you get this, and then if you integrate, you get this expression. And what do you get? Look at that expression. See, this is a constant. This and you can find out this constant is equal to, so rather I think this should be, this is 1 to the power n. So, this should be tau, I believe. So, this you can find out what will be the tau. Can you express tau in terms of, it is not k, it is, can you express tau in terms of as a function of nucleation site and growth rate. So, in fact, this type of derivation helps, because it helps you to analyze the experimental data that you collect, and it helps you to get a physical insight into the transformation process. And in that case, if you get a good physical insight by controlling the experimental parameter, you will be able to control the microstructure, and you will be able to therefore control the properties that you expect, and this property in turn will affect the performance of the material. Now, look at I mean, for that Pearlitic transformation, actually it has been extensively studied, and it follows this Johnson-Mehl Avrami equation. And here the assumption is both nucleation and growth rate, both are constant. That means, nucleation, there we assume that is a fixed number of nucleus in the previous model, and here we say that this is constant, n dot is constant and growth rate is constant. So, here also we can try and find out a small increment in this. So, at any instant there will be some amount of nucleation, and you can find out what will be the number of nuclei at any time. So, at any time that there will be certain number of nuclei present, and this you can easily find this out, because this is nucleation rate is constant. So, at any time t you will have, so if a time increases, say suppose we want to find out if this increases, say increment in extended volume during a time period t, how will you calculate? So, here there is a nucleation which is taking place, we can say n dt is the nucleation rate. So, what we can say that there is up to a certain time, this has been following this nucleation kinetics. So, up to that time n dot times t, this is many nuclei are already there, and these are going to grow, and then what you can do is you find out the average size of so this is 4 pi by 3, then g dot time, this is the average size of the nuclei. So, with this if you try to solve the previous equation which is shown here, I think what is missed here is another time t, because there is t cube, you will get n dot. So, this is nucleation rate. After that, here you have to insert a time t, which is missed over here. And so, here therefore, you will get this will be t to the power 4, and then you integrate this. If you integrate this, there is a t cube here. So, this is up to a time this dt, this no it is okay, that this is perfect, this expression is perfect, rather I made a mistake here. You need not, because up to a time, if this is the growth rate, so within this time so many nuclei will be forming, and what we are putting it is right in the beginning of the transformation process. This is the total number of nuclei which will be present at time dt, that initial, right in the initial stage there are so many nuclei, and this is the average size of those nuclei within that time, that small time t we are considering at a time t, and at time t you have certain number of nuclei, and what happens at time t plus delta t, the volume fraction will increase by this amount. And then what you do, you integrate this, since there is t cube, here you will get t to the power 4, and the expression comes out to be this. And here also what you do, you try to find out tau, this expression is given here. Now, look at the thing, earlier we got this exponent 3, here we get exponent 4. That means, this n is an indicator of the mechanism, it helps you verify the assumption that is followed, that it follows the transformation process. So, that way if you try to build up this kind of equation, knowing some that physical concept, it is possible to get a deeper insight into the process kinetics. And this is what has been done here, say in the site saturation model. If the sites are saturation model, this exponent is 3, whereas if you have a constant nucleation, constant growth rate process, then you get exponent 4. And similarly, as we it is possible to show with other subsequent mechanism, this exponent changes, and it also sometimes it also gives you the shape of your precipitate as well. Now, a quick look here at the growth kinetics, little detail, the Pearlite growth kinetics, and it was mentioned that Pearlite growth, it is follows through nucleation of cementite, at maybe this is an austenite boundary, a plate of cementite nucleates, and this disturbs the carbon concentration in the surrounding. When you have this nucleus this forming, when cementite precipitates out, look at that phase diagram. If this transformation is taking place at this temperature, this is the degree of supercooling you have. Here this is the amount of carbon ferrite can have, and this is the here ferrite is the stable phase, cementite is the stable phase, and when the cementite forms from austenite, it draws all the carbon from the austenite. So, therefore, the surrounding what happens where with austenite when the cementite forms. So, this is the carbon concentration in austenite which remains in equilibrium with cementite. So, that means if you have austenite grain over here, you have austenite, this austenite will be in equilibrium with cementite, and the carbon concentration in austenite near this cementite interface will be given by this, whereas cementite carbon concentration we know it is 6.63. So, since that much carbon has been drained from this neighboring region, here this carbon concentration drops, and with ferrite also it is possible to find out what is the carbon content at this ferrite that interface. At ferrite interface you can find out by extending this. This is the carbon concentration in ferrite which remains in equilibrium. This is the carbon concentration in austenite. Rather we should have maybe if there is a confusion, think about it, we write like this. This is carbon concentration in alpha near gamma that interface. This is carbon concentration in gamma near that cementite interface. So, there is a difference in carbon concentration. So, here you have more carbon. So, this carbon will diffuse inside also, here also you have 0.8% carbon, mind you. So, from here also there is a concentration gradient, it will start diffusing. So, therefore, what you have using the diffusion kinetics, you can find out the flux of carbon atom which will move towards this, and this will determine this growth rate, that is G dot, which will be equal to that carbon, which will proportional to the carbon flux. So, it will be proportional to the diffusivity, proportional to the concentration gradient, and this concentration gradient you can represent. This is the difference in concentration, this is the maximum difference. So, this will be the fastest movement from here to there, and look at this distance lambda. So, this is, you can say this is average lambda is this interlamellar spacing, that spacing between two cementite plate or spacing between the center point of two ferrite plates. And so, therefore, what happens is this growth rate depends on diffusivity, which is a function of temperature. We know that diffusivity is a function of temperature. Diffusivity is a proportional to exponential minus activation energy over RT. So, if the temperature goes down, the diffusivity becomes lower. So, there are two and again you look at this driving force for that carbon movement is controlled by this distance. So, higher the undercooling, higher is the driving force for that diffusion, and there are two different opposing factor. So, therefore, the G actually initially increases with the delta T, initially it will increase, but when you go down that diffusivity, this will become more predominant. So, it can become slow again, and that is why you get that C shaped curve that you get in the transformation diagram, and which is so this answers is why do we get C shaped time temperature transformation curve. So, this is the total expression for fraction transformed, and usually often we talk about that 50% that limit actually when you have this CCT diagram, that continuous the transformation diagram, it is often convenient to represent transformation kinetics by this C shaped curve, which represents actually this is temperature, this is time and this represents time for 50% transformation to occur, and which can easily be related to the tau. There can be some direct relationship with tau, and I leave this to you to show that to time to reach 50% transformation can be expressed in terms of nucleation rate and growth rate. So, this is the type of expression you will get. And to sum up here up to this is at low delta T you have driving force for both nucleation and growth is low, and at high delta T the diffusion rate becomes extremely slow. So, therefore, although the nucleation may go up, but point is this growth becomes very slow, and therefore, maximum a rate that you get is the maximum rate that you will get at an intermediate temperature. So, this explains the C shaped nature of the curve. Now, a quick look just now so long we looked at only the eutectoid steel. What happens if the carbon content changes? In that particular case, the nature of the CCT diagram will change, and what change will be there? So, here there will be some transformation even before the eutectoid temperature is reached. If you recall that phase diagram, so you have that if you recall that phase diagram, you have a region like this. Say hypoeutectoid steel is over here, hypereutectoid is this place, and both cases if you start cooling from this point, you pass through a region where from austenite ferrite will start precipitating first, and if this happens, then how will this transformation diagram be modified? Basic nature will still be the same, but what will happen is there will be another critical temperature. This is over this A3 only you have full austenite. When you heat it above A3, you get homogeneous austenite. A1, this is the temperature, eutectoid temperature, which is roughly around 723 degrees centigrade. And when you start cooling here, if you hold it isothermally, after some time pro-eutectoid ferrite will start precipitating out. So, you will get another line which represents start of ferrite transformation. Similarly, there should be a line for ferrite completion of that ferrite transformation, and which indeed is actually the start of once that ferrite is complete, then automatically this transformation starts, but this cannot start unless the temperature goes below 723. So, this becomes asymptote here, this becomes an asymptotic over here. And here also you can think of, if you have this type of isothermal transformation diagram, what will be the product? I will leave it to you to answer. And exactly, so what you have, you only have another additional line. Second is of course, this time value etcetera, that may change. It what will happen possibly, this will come closer, the nose will come closer to the origin, closer, and usually this time is a logarithmic scale. All this TTT diagram, they are drawn with a logarithmic time scale, and in a case of a hypereutectoid steel, this critical temperature is known as ACM, and here also this is 723. This line represents initiation of cementite precipitation. So, start for cementite, and here also So, nature is exactly same, and this nose with an increasing carbon content, you may find that these nose they shift to the higher temperature side. And rest of the part I am not going into the detail, which are exactly same. Here also you will get martensite plus austenite, this also is a martensite plus austenite, and this side is ferrite plus carbide. Now, let us see, we talked about bainite, and bainite is also an eutectoid product. What we can see, this is a low temperature eutectoid product. When your undercooling is very large, what happens, that diffusivity decreases significantly. Diffusivity of carbon in austenite is very low, and since this diffusion distance, so therefore, this diffusion distance, which is proportional, if you recall, is the diffusion, the time scale for the diffusion is proportional to root over del d is a diffusivity time t. So, if this becomes very small, very low, this becomes small. So, the carbon, the distance the carbon can diffuse is shorter. So, therefore, you get a much finer dispersion of carbide. Another thing, so the type of product that you get is little different. Now, in case of, and one can actually visualize that you have two sets of that C curve. This is the set of C curve which is for Pearlite, this is for Pearlitic transformation. You also have a Bainitic CCT, a Bainitic C curve. Pearlitic C curve representing isothermal transformation into decomposing austenite into pearlite. You have similar C curve for decomposition of austenite to bainite, which is this. And for plain carbon steel, often it is found that they overlap. So, that means bainite possibly this plot that see, this is the portion, you can say this is the portion of pearlite and this is the portion of bainite, they merge together. So, although we get apparently it looks one C curve, but it may be a superimposition of two such C curves. So, which is shown over here. And if you look at the bainite transformation, here also you get this ferrite plus carbide. Sometime in certain, particularly in low temperature, instead of cementite you may get a little different carbide called epsilon carbide. So, which is approximately 2.4 C. So, this has a little cementite roughly is Fe3C. So, here what you can say, here there is a little more carbon possibly. Now, this upper bainite, here also there is a distinction. If you look at the microstructure critically, there is a say if you look at pearlite, the top portion you get coarse pearlite, bottom you get fine pearlite. Difference is only in their scale of mixing. See, one is coarser, another is finer, whereas in case of a bainite there is a little more difference. And what is it? So, one is the way this structure develops. Unlike pearlite, there is some orientation relationship here. So, what happens in case of a bainite, some strips or laths of ferrite form at the grain boundary and this move, and as it moves the carbon starts precipitating as carbides, and these laths or these grains of fine, very fine grains or laths of ferrite, they maintain a definite relationship with crystallographic relationship with austenite. There is a definite crystallographic relationship between the alpha that precipitates out in gamma, and we will see this as we go on. and they form on definite crystal planes, and then these carbide platelets form on that lath boundary. So, if you recollect, so you have this ferrite that plates, and this is how the carbides, and this keeps growing like this, and you have this type of broken carbide platelets, and often they are so closely spaced that even you are likely to confuse this with fine Pearlitic structure. And if your transformation temperature is lower, say somewhere here, then you get a different type of bainite, which is called lower bainite, and here this shape of this alpha that nucleates, this shape is little different. This is needle type, and the carbide that forms may also be little different, they may be differently oriented, something like this. But here also there is a different orientation relationships that it follows with austenite, and carbides are in the form of very small rods, thin rods within this needles of these grains of ferrite that forms. And as we will go on, we will see often one makes get confused between the structure of lower bainite and martensite. And if you cool that sample from austenite, you quench it in water, we mentioned that you get martensite, and last class we talked about the structure, but it has few other characteristics which are listed here. Here there is no change in composition. So, obviously, there is no diffusion, no movement of carbon atom. It is athermal. The transformation continues as long as temperature goes down. Once the temperature goes below this, it starts when the temperature goes below a critical temperature, and once the temperature is crossed, it goes on, it continues as long as you keep it cooling. If you hold in between, then the transformation stops. So, this is the athermal character of martensite, and this is specific to iron carbon martensite what we are talking about. We will later see there are certain different varieties of martensitic transformation. There is a crystal different, it has a different crystal structure, and when this crystal structure forms, it is accompanied by significant change in volume, and which sets in a significant amount of stress in the structure. And the feature appearance, it depends on the composition, particularly if you are considering a 0.8% carbon steel. In that case, it is acicular. If the carbon content is lower end, then it has a lath character, acicular and lath. Acicular, it sometime you can say it is also known as a twin, or sometime we will see later. Say acicular is a needle like, and this is lath is like a thin plates, or you can say it is a thin strip with a definite orientation relationship with the matrix, and this orientation relationship acicular and lath, they have a different orientation relationship. Then comes the speed, it is very fast. So, that is the character, athermal character, and the speed is of the order of sound. So, that means the front moves at the speed of sound. So, therefore, if when the martensite forms, if it is possible to keep a microphone, you can amplify and you can hear the noise. So, that is, and since you are keeping so much of carbon in solution by force, it is extremely hard and it is also brittle, and this extent of hardness and brittleness will depend on carbon content it has. And a quick comparison between isothermal and athermal transformation. So, this feature we are very much familiar with, this is the isothermal S shaped curve, whereas athermal, what we are maintaining here, temperature, this is constant. Here possibly we say that cooling rate is constant, and transformation starts only when Ms is crossed, and once this MS crossed, this transformation continues, it continues like this, and it is extremely difficult to find out where the transformation is complete, and we will always see later that some amount of untransformed martensite austenite remains in the structure. So, usually MF corresponds to possibly 95% transformation. So, this is the basic difference between the two, and isothermal and athermal character. Isothermal will have the sheet type of shape, whereas athermal martensite you just get indicate these two temperature, and as you go down. So, this is percentage martensite increases, this as you temperature goes down, percentage martensite goes up. So, here it may be 10%, as you come here may be 90%. So, this is this character. Now, to sum a quick look at the comparison of the three Pearlite, Bainite and Martensite transformation, which are listed here. Structure, this has a lamellar structure. Bainite, you have two distinct, lath plus cementite, acicular plus cementite or epsilon carbide, whereas Martensite is acicular. In this particular case, a low carbon martensite can be lath martensite, but important feature, it is single phase. Both these are double phase, two phase mixture, but this is single phase. Here there is a long range diffusion. Here also, since precipitate forms, there is diffusion, but diffusion distance is low. So, that means root dt, that is length scale through which that carbon moves, this is low. Here there is no diffusion. Transformation characteristic, this is isothermal, this is isothermal, this is athermal. Orientation relationship, here there is none, whereas here there is definite orientation relationship between austenite and ferrite lath that forms. Here also there is a definite orientation relationship. You have one kind of orientation relationship in lath martensite, another kind of orientation relationship acicular or plate martensite. A quick look at the crystal structure. See, when martensite forms, initial structure is austenite, and when it forms, transforms into BCT structure, you can visualize this crystallographic transformation like this. You imagine, join these, then you get, there is one atom at the center here, and you have these atoms at the corner, but the dimension, this dimension is A, this dimension is A, whereas this dimension is A over root 2, this dimension is A. Now, look at this dimension, lattice parameter of austenite, lattice parameter of ferrite is this. Now, when it transforms into it transforms into martensite, what happens? This crystal structure changes slightly, and what is the change? This C axis, this particular axis undergoes 20% contraction, whereas this axis expands by around 12%. So, this is the net transformation, and this leads to a distortion which is called lattice distortion, which is called Bain distortion. And lattice distortion means obviously there will be change in lattice parameter, and lattice parameter change which are shown over here. This is the lattice parameter of austenite, it changes with percentage carbon, and this is the lattice parameter of we can say martensite. When the carbon content is low, this is alpha, in that case this here it is nearly BCC, whereas as carbon content increases, the C axis increases, because there is, we said that there is a contraction, no doubt, but still that contraction is not large enough, you know it. So, and whereas this is this expands, but still both are not no longer are not necessarily equal. So, therefore, what is happening here, this C by A ratio goes on increasing, and because of this there is a heavy lattice distortion. So, higher the amount of carbon, there is a more lattice distortion, and this reflects in the strength of the Martensite. So, that means, and Martensite very often in engineering scale is a Rockwell hardness, it is measured RC, this is around 64, and when it goes around 0.6, this 0.64 hardness is attained. Before that, beyond this, the hardness increase is nominal, which is not, does not show in Rockwell hardness scale. So, we stop right over here. Next class we will talk about little more about Martensite and build upon that. And what we have done today, to sum up, let us see summary. We looked at the nucleation and growth process critically. We derived the Johnson-Mehl Avrami equation, and we have seen based on that assumptions that time exponent it changes, which, and this n is an indicator of the physical processes that control transformation. We learnt about why the isothermal transformation curve has a C shape. We talked about Pearlitic, Bainitic, Martensitic transformation in little detail. We talked about the crystal structure of Martensite, and we also talked about some of the characteristic of Martensitic transformation, and maybe next class we will talk little bit about Martensite morphology and go beyond that. Thank you very much.